Hello, everyone. Um, I'm actually very excited to be here today. I really enjoy meeting all the Git handles from the community, which I I kind of see for the first time in person, and actually also people from my amazing team who some of them actually is the first time I meet after in person after 3 years. So um, so that's a very exciting day. But other than that, I would really love to talk about the amazing work that we did in really building the largest cluster to date of OpenSearch, and also to share a lot of with the community a lot of the architectural and in kind of lessons that we learned and how we can do better. The more we go on bigger and larger scale. So, okay. So just a little bit about myself and how I got to deal with OpenSearch. So I was doing startups and then I was working for Amazon EBS. Amazon EBS also had like lots of big data problems. Um, then when I moved to OCI, I was architect and tech lead on the logging, audit, the observability stack. And then the amazing thing happened. I learned that we planning to launch the open source, like a managed open source service, and that was my calling. So that's kind of the short summary of that. So one interesting thing, I think a lot of people might ask, like, why even bother? Why do a 750 node cluster in the first place? So the truth is that you know they're actually when we look at what customers do with like their clusters, so some of them they keep piling more and more and more data into it, right? It could be log data, time series data, and really some of our customers they not only do that, they also want to keep that real-time kind of online usage. They want to expose this snappy, super fast API with latency of just a few milliseconds. And and in theory that's great, right? The system can do it, but for us as a managed service, it introduced kind of a lot of interesting challenges that we're gonna see soon. So the mystery customer we're going to unravel here is NetSuite. It's I think Jim, our keynote speaker, he mentioned that very briefly. So to give you a bit more of a concrete data on that is they actually wanted 750 nodes of data nodes. They had 3 cluster managers, and they want to have a overall of 6 petabytes of data in that cluster with the ability to scale to 30 petabytes of data over the next 2 years. Okay, I mentioned earlier, really the one of the harder challenges for a managed service or for any team who run OpenSearch in production is the problem of vertical scaling. So what does vertical scaling means? It means I want to take, say, a cluster of OpenSearch with some data nodes, and I want to change the specs. Like I don't want to just add new nodes, but I literally want to change the CPU type, the instance type. I want to change the kernel on the machines. Um, I want to increase the RAM, whatever, right? Anything that sort of changes the spec or like the instance type or anything like that. Um, the the approach that is kind of very common today in managed services, and that's an approach we also adapted initially, was the blue-green deployment, what we call in our team the hot replacement problem. And the challenge really when we do all that stuff is how to keep the performance and the availability. And so, when we say performance, we really talk about the query latencies, how to keep that really as least impacted as possible. So before we really kind of deep dive, I'm gonna just establish some baseline with some terminology. I apologize if for some of you it's like too basic, but it never hurts to kind of for the protocol to make sure we have the same language. So OpenSearch index, a lot of you know, collection is a collection of documents. Document is a collection of fields, key value pairs. Shards are the physical partition of the index, which is in the of the OpenSearch index, which in fact is a Lucene index behind the scenes. Then we have the cluster manager. Cluster manager actually holds the state, the metadata, and the routing table that says each shard, where it's at, and how to get there. A concept we're going to use a lot, and we even used in the title of the talk, is allocation. So when you think of allocation, you can really think about it as a lot of different things. So one of them is assignments. What is assigned to what? Relocations, how I move shards between places, between different nodes, and policies, right? Which shard is allowed to be allocated? What is their policy, and what are the states of these allocation processes, and all kind of stuff like that. So just again, start with some very simple examples, so we can kind of have those concepts kind of ingrained deeper. So let's look at these very simple cluster. There are like 4 data nodes here. We have 2 indices, A and B. We have shards A. So the shards are A0, A1, B0, B1, and B2, and we have 2 replicas for each shard. So we'll mark the notation we're going to use. We're going to mark the primary shards with a green, and the replicas will mark with a white color. So in this case, you see there's like 4 nodes, and you can see the shards where they're placed right now. Now let's say we want to create a new index, and that index will have 2 shards. One is a primary, one is a replica, right? That index is C. So the first thing that happens is those shards will actually show us as unassigned, right? So we first need to decide where those shards will be assigned. So the default logic in OpenSearch is really to try and balance the shards as much as possible. So it will try to make sure that every node has the same number of shards assigned to it. And after that, a secondary rule, also very important, is to make sure that we don't assign the shard with its replica on the same node. So let's say in the previous example, right? I'm just gonna go one back. So we would expect C0, right? Both shards, one to be assigned to node 2 and one to be assigned to node 3, because that's how we're gonna distribute things evenly. Now, another thing we can do is we can leverage something called an allocation decider. So what does an allocation decider mean? It means we can override that default logic in all kind of interesting ways, and sometimes very useful ways. One very common example is we can set a disk threshold. So we can have an allocation decider that sets a disk threshold and says, okay, if the disk threshold, like if we fill the disk more than 85%, don't assign any more shards, don't allocate any more shards to those nodes. So in this case, for example, if node 3 has 86% of disk usage, then we will not be able to distribute shards evenly across the nodes. Okay, so let's say, let's assume for a second we don't have the limitation with disk usage earlier, and we just try to like start the allocation process of the new index that was created. So the primary shard C0 is going to be assigned to node 2. Node 2 is going to detect, okay, I have assignment. It's going to pull data from the cluster manager that says, okay, this is the state you need to have. And when it gets the assignment, it's going to create a new index, because that's a new primary shard. Okay, and when it's done doing so, it's going to notify the cluster manager that it's done. The next thing is going to be the assignment of replica. So now we need to assign the replica, and we're going to assign that to node 3. And in node 3, the replica thing is actually a bit more interesting, because technically it's empty, but we're not going to create a new shard, like a new Lucene index, like we did with the previous primary. We're actually going to start a recovery process. So we're going to start the recovery process from the primary shard. When the recovery process is done, then the node 3 will report the status to the cluster manager that the state is started. So we can now use those shards. Okay, so now we kind of, that was all nice, but let's talk a bit, how does that really relate to the vertical scaling problem that we mentioned earlier? So with the vertical scaling, one way to do it is, as we mentioned, is a blue-green deployment. What does blue-green deployment mean? Blue-green deployment means I have one cluster, I want to have another cluster, or I have one set of nodes, I want to have new set of nodes, and I want to move everything from old set of nodes to the new ones. One way of doing that, which again is very popular, is something that is very common, is to really just start new nodes and let the replication and allocation and recovery mechanism do the hard job for us. So what does that mean? Let's say we have these 4 nodes, and we want to start node 5 with a different kernel type, and we can start node 5. And then what's going to happen is those processes that I mentioned earlier about the relocation, that we're going to try and rebalance, the OpenSearch is going to try and rebalance the shards. How is it going to do that? So the way it's going to happen is we're going to assign, right? Say we have A0 replica, we're going to assign now into node 5. And when we assign the shard into node 5, we're going to start the recovery process same way as we did with the new index creation. But this time, but remember that the recovery always happens from primary. We're going to try and copy the data from primary to the new shard replica on node 5. And later we can eliminate the other copy from node 4. Okay, so a little bit of, when we say copy, it sounds very, very simplistic. It's actually a much more complicated process than that. So just on a high level, what does that mean? First of all, Lucene, the shards, they're actually Lucene indices. Lucene indices have segments. Segments have multiple files in them. When we try to copy a segment or a bunch of files from one node to the other, we have to make sure they're not deleted. So the first thing that really happens in that process is that we have, like on the source node, we have to really create a deletion policy that makes, hey, don't delete those files. Then we start copying them to the new node. After we copy them, then we need to copy the transaction log, the translog, and we keep copying the translog and replaying it on the new shard. And eventually we're going to say, okay, now we're good and we can move on. And now we have actually a functional replica. Okay, so that's, again, this was all background. And so now we know what blue-green deployment is. How does that relate to the shard allocation process? Now let's talk a bit about what we did and how what we did to help the customer actually made it a lot harder for us. So one thing that we really wanted to do for our customers was really to introduce the ability for customer to choose exactly how much cores and RAM and disk they want. We didn't want them to really choose from pre-baked shapes. So we did this thing called the flex architecture. So the customer, if they want to just increase by a single OCPU or by a single gig of RAM, the specs of their cluster, they can do so at any time. And we thought that's a good thing for the customer because in this way, the customer can really pay for exactly what they need, and they don't have to sort of try and bulk put things in like buckets of like, okay, now I need these nodes, and now I will need this one, and I'm not gonna really need this, but I'm gonna do it anyway. So that to achieve this, we had 2 things implemented in the architecture. So for our data nodes, and actually all our compute nodes, we use the OCI has this type of node called the flex shape. So we can dynamically increase the OCPU and RAM count. And for the storage, for the disk, we use block volume, which also on the block volume, we can dynamically increase or decrease throughput and size and so on. So we thought it's actually a good thing, and we're very proud of that. However, while we're trying to do the right thing for the customer, again, it's a managed service. So the expectation is really that things will work, especially when we do a vertical scaling. Things need to be as seamless and as possible and have a minimal impact on customer. So one thing that is important to keep in mind is when we say, hey, we just copy data from here to there, it's actually copying of data has a cost. There is always a cost associated with it. So if we just do this mental exercise of like, what does it mean to copy a few bytes of data from node A to node B? So in our architecture, it means we first have to read the block volume. So the block volume is not a local disk. So that means we have to take some of the network bandwidth by reading the block volume. The other thing that we now need to do is we have to read it. So the operating system obviously will cache it in the RAM. Then it will have to get to the JVM. Then we have to send those bytes over, which also has a network I/O cost involved with it. So both network I/O and CPU are a cost that we have to factor in. This is not completely free. And that might not be that does not by itself disqualifies, the approach. But given that we allow the customer to be so flexible, what if like I'm a customer and I decide that I want to have a data node with just a single core, but 3 TB of disk storage? What's going to happen then, right? With that approach, with those cost model. So a quick calculation, we realized that that might not always be very feasible for a customer to do so, because the flex shapes, they actually have a network I/O bandwidth that is proportional to the number of OCPUs. So in that case, if the flex shape has by default 0.8 gigabit per second of network bandwidth per OCPU, then that means in our case, consider that things are not super optimal. There is like TCP packets and all kind of inefficiencies with transmission. Plus, the customer themselves, they need to do things, right? We cannot take all their bandwidth to just copy things over. So we realized that that can actually take more than 25 hours to replicate that single node. So in 25 hours, a recovery process that takes 25 hours is actually very, very suboptimal for customer. It's not something that we could live with as a decent customer experience. So then one of the reasons why we went to block volumes in the first place was actually twofold. So one of those was related to the flexibility, right? The flexibility we can give to customers. But we were all also a little bit selfish there, we must admit, because from architecture perspective, it means that we can do things that actually are easier to do when you separate the storage from compute. And what do we mean by that? So the quick follow-up that we really had to do on the blue-green deployment was do this design, which we call the blue-green deployment V2. And that means in this approach, instead of trying to leverage the operating system and the native shard allocation mechanisms of OpenSearch to replicate the data, we actually use the block volume replication directly. We actually do block replication. So in this approach, we get a few benefits that are actually very important to solve the first problem. So the first benefit that we get is that we don't have to add a node and then another node and then wait for rebalancing and all that stuff. No. In this approach, we can create a whole new cluster, a whole new everything, replicate, just do block clone to the new cluster. And then when the time comes, when we decide the new cluster is fine, we can just switch traffic to it. So it's a transactional switch. And that's actually very convenient in case we have to do any failover or rollback. The other thing that we get from that is even more important. So the other thing that we get from that is that there is no performance degradation, because when we clone the block volumes, we actually do not degrade the network bandwidth of the instance. We do not take OCPU resources from the instance. We do not involve the JVM. None of that is happening. And actually, that is very, very good for us on all these vertical scaling hot replacement scenarios. The other thing that was also really, really important there is it doesn't need to take 25 hours. In fact, the block volume ability to the block replication is always proportional to the block size. So sorry, is always proportional. The network bandwidth of block replication increases with the size of the block volume. So it's always deterministic. So we know that in 5 to 10 minutes we can really replicate any block volume to another node. And then we know we don't need to wait 25 hours. So that was actually working for us for quite a while, and we were very proud of it until we got a new customer. And the new customer that we got, that was NetSuite. They came with these requirements, right? We want 750 data nodes, and we want each data node to have 9 terabyte of disk storage. Now, the other thing that was interesting, and we thought, yeah, why not? Let's do it. When we started ingesting their data, we realized we're really looking at over 180,000 shards. So that was quite a surprise, and that was okay. I mean, we're not deterred by the challenge. So we ran the basically we ran the vertical scaling workflow. So what can go wrong, right? So we start the vertical scaling workflow. We create a brand new cluster. Everything is replicated. We're super happy. And the new cluster is red. So obviously a great disappointment. Okay, so more than the cluster is red, we see all kind of other disturbing things on it that's occurring. So almost all the shards are showing as unassigned. So remember, unassigned means that they're not assigned to any node. And another thing that we see is that nodes keep coming and going out of the cluster. So only a very, very few nodes actually remain part of the cluster, but even they eventually drop out of the cluster. And the cluster doesn't stabilize. We can wait like this for hours, for days, and it never recovers. And even more so, we eventually find that we start seeing these beautiful messages on some of our cluster managers. So they actually go out of heap space memory. Okay, so we can definitely. So before we really do any sort of deep dive, you can argue that there is a lot to be done, right? Even before, like, yeah, sure, 750 nodes. Let's try to take a step back and reason for a second about what we did and why that could be a problem, right? So first of all, whenever you bring up a whole new cluster, right, with so many shards on it, with so many data nodes, the first thing that happens, right, is that those nodes, they try to join the cluster manager, right? They try to say, hey, I'm part of the cluster, register me, please. And the thing is, especially with this situation of 750 nodes, they might not do so at the same time. And when they're not doing so at the same time, then obviously one node says, hey, I'm here, and here's my primary shard. Another node says, I'm here, here's my other primary shard, but the replica haven't joined yet. So what would the cluster manager do? Obviously, it's going to try to shuffle things around to start recovery procedures. And then more nodes join, and then more of that happens. So that makes sense, right? Like something that could be a problem. Um, the other thing, so that's something that, okay, we can try and work with. So there are actually some very well known fixes to this problem, right? This is nothing really new right now. And really one of the well-known recommendation in that case is, hey, you need to disable allocations of replica. So the cluster manager is not going to try to do any recovery until all the nodes join. Once all the nodes join and you can see all the primaries, then the cluster will be obviously in a yellow state. So yellow means the primaries are there, but not all the replicas are there. And then after we have all the nodes and all the shards physically present, then we're going to try and enable replica allocation and hope that the cluster manager is able to find all the replicas and reconcile, and we can avoid any sort of unnecessary I/O shuffling and recovery processes. And by then, we hope the cluster will be green. So let's try it. Let's try it on our... So we go back to our huge cluster. We disable allocations. I mean, of course, we replicate the new cluster. We disable allocation, so it's not going to try and create any chaos. And it doesn't help. We still see that our cluster managers are showing the out of heap memory errors. And even more interesting, we see it's only happening on the leader. Only on the leader of the cluster managers it's happening, but not on the other cluster managers. Obviously, when the leader dies and a new cluster manager is elected as leader, which also goes out of memory, and eventually nodes also start disappearing and rejoining the cluster because every time they have to discover the new leader. Okay, so we can see this, but another interesting fact is when we try and enable allocations, we're like, okay, disable allocations didn't help. Let's enable them back. It's even worse. Like we see even more nodes dropping, and we never go to green or yellow or any nice color other than red. Okay, so obvious thing to try. Let's try to increase the heap size, right? Like what can happen, right? Just increase heap size, increase RAM, put some money on the problem. Maybe it will go away. So the nice thing is that it partially went away. So we disabled allocations, increased heap size, and now our cluster comes back up, and it's in yellow state. So we obviously feeling a lot better. So we're onto something. And then the cool thing, our cluster managers are no longer crashing, which makes us feel great. So okay, let's enable allocations. Hope for the best. Now it will surely go green, and no, everything dies, everything goes red. Cluster manager is out of memory. No luck. So okay, so there is no choice. We have to look at the heap dumps. We have to understand what's going on. We cannot just add some memory and hope that the issue will get resolved by its own. So when we look at the heap dumps, we find some interesting patterns there. The first interesting thing that we see is that if we look at how the cluster manager operates, so whenever something changes, it's trying to do something called a reroute. It's trying to calculate the best state of the world. And when new nodes join, it's also trying to send them a question of, hey, for this shard, tell me the status, right, on this primary shard and stuff like that. Or for this replica, tell me what's going on with this replica. So it can actually decide whether it can be used, reused, or what to do with it. And that makes a lot of sense. And what even makes more sense is that it's storing it in a cache. And that cache is actually what's actually showing us in the heap dumps, flashing red, taking all the heap memory space. So what you see here is a 16 gigs of RAM that's taken for cache, just to cache information about primary shards. That's when the allocation is still disabled. Now, if we're going to at this point enable allocations, we're going to more than double the size of this cache, because once we enable allocations, the caching of the replica information takes even a lot more memory. Now, the interesting thing about this cache is that it's unbounded. There is nothing that really rotates things in and out of the cache. So what that means is that you eventually exceed the memory limits. So we thought, okay, I think now we understand We can fix this, but first let's just make sure we can actually it's still feasible to get the cluster to our customer. And okay, let's put money on the problem. Let's get half a terabyte of RAM and hope for the best. And well, that worked. And but still, nodes are not joining. No, nodes are still not joining the cluster. So what we see then is something interesting. What we see is that okay, the cluster manager is no longer crashing on us, and that's great. But once we enable allocations, we do see nodes start dropping out of the cluster, but no more out of memory errors anywhere. What we do see instead is that the data nodes, they start reporting issues with reaching the cluster manager leader. We look at network looks okay. We don't see any issue there. However, what we eventually found after digging is that the TCP queue on the leader is actually huge. It's humongous because it's also shared with all those async fetch requests that the leader is trying to send to all the nodes to gather information about the shards. So the solution is dead simple. It's actually increasing the leader check timeouts on the data nodes. The default was 10 seconds. When we increase that, it works. And we finally get a green cluster. So there are a few things that we do want to do to get things better going forward. So obviously we're not intending to keep saying, hey, for 750 nodes, let's just provision a preposterous amount of RAM on cluster managers. So a fix that we actually already implemented and we're actively testing is to really change the implementation on the gateway allocator to really make the cache bound. So far, it looks really good, and we hope that we can eventually contribute it back to the community if anyone else has this use case of trying to kind of stand the humongous clusters. Um, the other thing is that we found was that the leader check timeout right now is a static configuration. So one of the things we did actually when we were trying to debug it is we actually changed those settings to be dynamic. And this is another thing we think we can contribute back. So it's easier. There is no reason right now that we see for this to be static. So more on the kind of high level of the replication aspect. Ideally, we would not want to be in the business of copying data at all. So another thing we're exploring is really the possibility of using multi-attach to completely remove the need to copy data and deal with these kind of problems. One thing I want to say for last, I really want to thank my great team members. So two of them are here, Egesan and Dimitri, and Fong is bathing in the sun in Florida, but we still love him for that. And that's all.